Hey, welcome back again. We're on our next video here, and we are going to finish up now with the design of the circuit. We left off here where we had this here PNP current amplifier feeding an NPN, which turned that LED on. I have this here NPN transistor as dedicated to run the LED only. I have the same setup down here that's going to be for feedback current. What I want to do is I want to make the feedback current separate from the currents that's happening up here, and that's why I'm going to use an opto-isolator here. Another thing is what I'm going to do is I'm not going to feed the feedback current directly back into the input of the Schmitt trigger. I'm going to keep the base input clean of any kind of feedback currents. Rather, I'm going to put it in series with the base current, which means is by using this opto-isolator, I'm going to have a ground signal coming over, and it's going to feed into an active component that is going to take the place of the pull-down resistor that was in series with a potentiometer. That way there, the signal now will be coming in series with the potentiometer, which then will feed into the base over here. What that mainly is going to do is, since this is an NPN transistor that is being used as an active pull-down, by putting a negative signal into its base, it's going to drop it. It's going to start bringing it to cutoff, therefore allowing the base voltage here to rise positive. I also removed the 1K resistor on the positive rail here, and to keep that from burning the transistor, I put a 10K ohm resistor at the base here to give that its current limiting factor there. And by removing this 1K out of here now, I have more positive flow to get better input as well. Okay, so now what I want to do is I want to explain one more thing too. Over here on my last time when I was drawing this in, I never put a collector resistor in here. There has to be a collector resistor in here in order for this transistor to be biased on properly. Because I did not have this collector resistor in here, whenever I hooked this input up, I got some erratic responses at the circuit. And I'm going to show you what happened and how putting this resistor in here took care of that. We are at the bench here again. I have my circuit working here, and I have the square wave. I can increase it and decrease the speed. Everything's working good. Now, for the last couple of days, I've been running this here problem. Now, I'm ready to put the feedback in here, and this feedback is what's needed, that as I shown before in the schematic, so that I can have the torque control. So here's what's taking place. I put the feedback in, and look what's going on. Look what's happening. I keep on getting these here feedback oscillations. The motor keeps on speeding up, it goes back down, speeding up, goes back down. Automatically, I'm getting oscillations going here. So I began to think about what's going on, what's causing this thing to oscillate. For the last couple of days, I couldn't figure it out. I was looking at it and trying everything, putting capacitors in there. I tried everything. Now, when I removed the feedback, everything's back to normal again. Everything's back to normal. Perfect. So that's where we left off at the video the last time. Everything's working normal, perfect. But when I put the feedback in, that's when I was getting the oscillations. So here's what I did to remedy it. So what I kept on doing, I kept on looking at the circuit here. I put capacitors in there. I kept on just thinking logically what would cause, how can you stop the oscillations. I put bypass capacitors. It worked a little bit, but still was not working properly. I just could not get it. And I looked at it and looking at the circuit, looking at it, experimenting, and then I decided to look at the schematic. The schematic, and began looking at the schematic, and this is why it's so important to have a schematic to look off of when you're trying to troubleshoot a circuit or when you're designing a circuit. I knew it had to be someplace in this area here, because that's where the feedback is happening here. I began to look at this, and I began to realize something. I'm saying, okay, the emitter is positive with respect to the base. The base has got this negative input here. It's got a negative bias here, base emitters. I began to look at the collector here. I'm saying, wait a minute, that collector voltage is hanging here. The collector bias is really through a active component here, a non-linear component. The base emitter junction of these transistors are diodes, and a diode is a non-linear element. Therefore, remember, it has a curve to it. So there has to be a 0.6, 0.7 volt drop across the base emitter junction before this can even start conducting. So what's happening, I began to look at that and think, wait a minute, if there's no bias on the collector, this transistor is not acting like a transistor then either. It's acting as a diode. It has to take a very strong input voltage in order to get a collector voltage out here to bias the base emitter of this. This is not even biased on at all. It has to have an input voltage to it. I want this transistor to be running in a linear mode. It has to be in the active region, not in the cutoff region. Without the collector resistor here, there is no collector to base bias. There is no reverse bias, therefore the transistor is not acting in the active region. It's still in cutoff. So, by putting a resistor in here, and I put that to ground, I can now develop a voltage. First of all, I have now the biasing necessary. This transistor is now turned on. It's now linear. That means any kind of an input going into here now can be amplified. It doesn't take an input to turn it on like a switch. It now takes an input to amplify it. And that's the whole key right there, putting that resistor in there. Very important to make sure that your transistors are biased properly. You cannot bias with a non-linear component. You have to have a DC bias. They have to be resistors. Now let's go back to the circuit and see how it works now. Circuit board here. Here goes the feedback. And there goes our oscillations. Alright, here we go now. What I want to do, a 1 kilo ohm resistor from ground to the collector of this tip 42C, and that took care of it. Right there it is. Now I can adjust the voltage here back and forth, and there's no oscillations. Alright, that took care of that. Now, let's try a feedback. Let's actually put a load on the motor and see what happens now. Okay, now we got another thing to contend with. We don't want that to speed up like that. We just want to just increase a little bit at a time. Okay, so what we have now, a small input. Let's go ahead and slow this down to real slow. And let's see what it does now. Here we go, real slow now. And let's put a load on here. Look at that. Wow. So that means then we got some more work to do on this. Alright, let's think this through again. What would cause that? There must be some sort of a input signal from this here feedback now that is overly driving the input transistor. So let's go back to the schematic. The schematic again. Now, let's think this through. If it's overdriving, if the input signal is now overdriving, the more load I put on the motor, it just ramps up. So everything's working good here. If we're getting our input signal through here, everything's biased properly, no more oscillations, but it's ramping up too quick. Why? Well, let's think this through again. If we have the input signal down here, that means this diode must be coming on very sharp, very quickly. What would happen if we were to increase the current limiting resistor to this diode in the opto-isolator so that it will not light up so fast and so bright at one time, but let's put it in a very linear region so that its illumination to the base input will be a very gradual transition. All we got to do is take the current limiting resistor and increase it. Right now I'm using something like 1K ohm to get a good brightness here. Let's increase this to what I have written here, about 62K, and let's see what happens now. Okay, so here's the 1K into the opto-isolator, and let's change that out for a 62K. There we go, 62K right here. And that goes to the positive side of the battery, and this goes to there. Now we have a 62K ohm in series. Let's go ahead and put this on low speed, and let's go ahead and put a load on the motor now and see what we get. Okay, let's check and see if we're getting any kind of a pulse here. Okay, it's increasing. Good. That took care of that. Okay, so we know now that we can increase the resistance for the up to isolated LED so that we can get that LED illuminating in a linear way. Now there's one more thing. I like to have more sensitivity on that. See how that wasn't very that didn't give a whole lot of input back, feedback. So the only thing left now is go back to the schematic and find out what other resistor can we change in order to get a better feedback, to get us larger feedback now. Look at the schematic, and here we go. Let's take a look at this again. What drives all this now? Well, it's this PNP transistor up here. Now we have this in a linear region, but is it amplifying to the largest amount of amplification it really can? Is it actually maybe down too far on the load line? Is it possible that it's not really getting a lot of amplification? Well, let's check and see. I originally have a 240k ohm resistor in the base here. If I were to decrease this to here, remember now, this transistor is a PNP, and so the more current that we get into its base, the harder it's going to run. The more linear it's going to be, the more currents that's going to be able to flow through the collector emitter to pull more positive on here. So right now the 240k ohm resistor on there, if I were to change this to 180k, what I did before is I just did some experimenting with my resistor substitution box, and I found that 180k took care of that. So let's go ahead and change this resistor from a 240k down to 180k and see if we can get a better output from here now to give us a better square wave, so that the width can go a little bit larger now because we have more amplification here now. Okay, so I'll remove the 240k from the tip here, and I will put in this 180k, which gives it a heavier base current. It turns it on. And let's go ahead now and turn our circuit on here, and let's give it an input now and see what we have now. Oh, that's nice. It's a lot wider. We get a nice response. Okay, let's just go ahead and just do a little bit of work here and see what we got going on here now. Here we go. You hear it speeding up? Let's go and put it down slow. Let's put it on a very slow range here. Now I'm cutting steel, so it could grab on the bit, and it's not a very sharp bit, so it could grab the bit, but we're trying to... Okay, here it's nice and slow. And let's look at the waveform. See, it's nice and linear. Now I'm catching on a... I have to speed this up to get past that. Speed up to about there, just to get past that where it's catching it. Okay, now I'll turn it down a little bit. I had to break that there chip off there. Now, there we go. Nice chip it's making. Look at that. And you can hear the motor. And there's the waveform. And that's what you want right there. So I would say then, at this point, like I said, I'm cutting steel on this here. That shows how we have this all designed, and we showed also how to troubleshoot the circuit to get it working properly. I now have this where I want it at, that I can actually put this board now on top of this and get all the wiring hooked up, and I can now have my lathe back. Now I will say this is definitely not a good torque feedback. This is just my way of doing it is just taking the current off the motor, more or less. That's why professionals use tachometers and microprocessors and everything else that's necessary to get a good feedback. But this is going to work for me for what I want to use it for. The way I use my lathe, I can just work with this, and I think it's going to be good. Plus, by me using a breadboard on this, I can always build new circuits and change this out anytime I need to. I'm not going to make this to a printed circuit board. It's going to be all on this breadboard. And then I can put new breadboards together as I learn more about how to make better circuitry for this. I can just keep on adding on and stuff like that. Okay, so the next video, if I do another video on this here, will be the finished project of this here, getting it all wired up and everything, and getting the lathe back to working again. So that's all for right now. Thanks for watching. Bye.